I want to start this week with a rehash of an exercise on lists and iterators from about 6 weeks ago. And the reason isn't because suddenly lists and iterators are a lot more interesting. Nope, they're just as interesting as they always were, which is to say very interesting. It's because due to the extra difficulty of working with lists and iterators, I think it really helps to motivate the main topic for the week, which is something called functional programming. I'll just write that in there. Functional programming. That's one of those terms that seems to have no meaning whatsoever. Of course, programs are functional. That's the point. Or do you mean programs that have functions? Because we've been writing those since 1.11. What the hell is functional programming? In fact, it actually refers to families of languages. The languages you know so far, which are probably C and C++, are examples. Usually they'd be considered members of a family called the imperative languages. And imperative programming languages usually are considered to be defined by assignment statements. And we know already assignment statements are a really big deal in C++. That's one of the reasons we have those laws of assignment statements. The programs really only get stuff done as a result of assignment statements. And imperative languages typically rely on assignment statements to modify the state of variables as the program continues. And they often have things like structured control flow, such as for loops and while loops, and those rely on the state of the program changing and asking questions like, oh, is I less than 10 at each step? And I might change over time. And we might think, and I think I'd forgive you for thinking, that after learning C and C++, you might think, hey, every language is like that. There are assignment statements and if statements and for loops and while loops, but that's not true. There are entire families of languages that do everything differently. There are, for example, languages out there that do not have assignment statements at all. Classical functional languages, so one example of a functional language, a very old one, is called Lisp. Classical functional languages often don't even have assignment statements, nor do they have for loops and while loops. You do everything. The key unit of the program isn't a variable that you can assign to, it's a function. In functional languages, functions themselves are considered to be data. You can pass them around to other functions. You can use recursion instead of loops. We already saw a taste of that last week about how we can often use recursion to great effect in places we otherwise would use loops. In a functional language, the idea of an assignment statement is sort of weird. The same way to many of you that the idea of a function being data is sort of weird, or even the idea of recursion is sort of weird. And it's a matter of, just like how if you know English, maybe you can understand certain grammatical structures that might show up in a language like French or a language like German, but there are languages on earth that are completely different from those languages, which are actually closely related. If all you've ever heard of is English and French, you might get an idea that all human languages are similar in those ways. They all have the same basic idea of what constitutes grammar or what sounds are used. And the same is true of C and C++. They're about as similar as maybe French or German or other languages, the Romance languages. But there are other languages that are completely different. But it turns out there are some reasons why functional programming languages can be helpful even in an imperative setting. And C++ has added some functional programming features in the last decade that we're going to find very useful. And that is the topic for this week. Because obviously I don't want to just drag in new material just because I like it. I want to drag it in because it's useful. I first have to prove to you that none of our existing techniques seem to work for the problems that we are going to solve using our functional programming techniques. And to do that, I'm going to revisit this exercise from a few weeks ago, which was tedious enough that we can agree that the type of redundancy we're going to observe is something that we want to avoid. All right. So I have these two list objects here, and they have 3 elements each. I've drawn them down in the lower right corner, and I'm going to call this function called pair up. I pass in both lists. The functions I'm going to write in this video will all assume that the 2 lists I pass in have the same size. In the event that the lists have a different size, the function will throw an exception. Okay, but these 2 lists do have the same size. So what does the pair up function do? It takes 2 lists of ints and it returns a new list whose elements are pairs of ints. And each element of the new list will be a pair of the corresponding elements of the 2 input lists. So the first element of the result will be the pair 610, which are the first elements of L1 and L2. The second element of the result will be the pair 116, 106, the second elements of L1 and L2, and so on. Okay, that's what the pair up function does. I will just run that to show that it apparently works. The compiler is complaining, and rightly so, because the warnings it's giving are that I haven't written certain other functions. Those are innocuous for now, though. I try running it, and there they are. They're the 3 pairs in my output list. So LP is the list that was returned from pair up, and I'm just iterating over it and printing out p.first and p.second for each pair p. All right, the point of the video is to write a bunch of similar functions. So the first one I want to write, I'll just uncomment the testing code for all of them. The first one I want to write is called sum element-wise. And it's actually this function that we wrote completely in an earlier example about 6 weeks ago. And so what this is going to do is take two lists, just like the pair up function, and compute one new list of just integers. It's not going to compute a list of pairs. Each element of this will just be an int. And the element will be the sum of the corresponding elements of my input lists. So in this case, the sum of 6 and 10 is 16. The sum of 116 and 106 is 222. The sum of 187 and 111 is 298. So again, sort of column by column, we take our input lists, look at the pairs of elements, in each column, and then perform some operation. In this case, I want to sum them up. In a minute, I'm going to write also compute their difference, so subtract them instead of add them. I'm not going to bother writing that down because maybe you can see what I mean. And then finally, compute their maximum. I guess I might as well sketch that out. L max. Okay, so what's the maximum of 6 and 10? It's 10. What's the maximum of 116 and 106? It's 116. What's the maximum of 187 and 111? Okay, so it's 187. So again, I'm just going to go column by column and look at the pair of elements in the same position of each of the two input lists and use that to generate the element of the result list. So all of the functions I'm going to write are very similar. Let's go up and take a look at the pair up function. Okay, so there it is. And it's pretty ugly. And some of the ugliness is because of the use of the STD pair type, maybe. But there's a lot of machinery I'm going to need in all of my functions. Okay, I compare the sizes of the two lists. Fair enough. I then create an iterator over each list. When we did this exercise 6 weeks ago, I pointed out that there is really no way to avoid iterators here. You can use a for each loop for one of the lists, but you need at least one iterator. And I've claimed that using two iterators, although maybe more iterators is a little bit more confusing, using two of them allows us more symmetry between the two lists as I work through them. So I make an iterator over each list. Because I know the lists have the same size, I can just iterate until one iterator becomes invalid and then walk both iterators along the same amount at each step. Okay, so then in the inside of this loop is where I actually create the element of my result list. I use make pair to create a pair of whatever iterator 1 is pointing to and iterator 2 is pointing to, and then I add that to my result list. This could be done in one line, but whatever. I'm trying to make it look more obvious. Okay, so I have my pair up function. I now want to write my function to compute the sum of elements, the element-wise sum of the two lists. So I'll go down here. I will actually copy and paste it just to prove how much redundancy there is. The only major difference up here is that I'm computing a list of ints, not a list of pairs. And then the other difference happens down here, inside the loop. The machinery of the loop is the same in both functions. It is going to be exactly the same. Okay, so what I do instead of creating a pair object, I just take what iter1 points to and iter2 points to, and I add them together, and I push that into my result list. And that's it. That is the only other difference between the two functions. Okay, let's compute the difference element-wise. So I'll just copy this. I guess I'll just copy the inside of the function. And list difference element-wise doesn't even have a different return type. So unlike the previous case, I don't even have to change this line. All I change is this one thing. Notice again that the different behavior is happening inside the loop. Okay, so now we'll go down and compute the maximum of two lists element-wise. There we go. Okay, this is a little bit different. So here I want to choose which of these two elements to keep, the one from list 1 or the one from list 2. So I'll use an if statement. There is a way of doing that without an if statement, and I'm sure if you want to be clever, there is a clever way of doing it, but for the sake of being clear, I'll use an if statement. Okay, so if the value that iter1 points to is larger, then add that to the result list. So result, I'll push back, iter1, and then otherwise add the value that came from iter2 to my result list. So push back iter2. All right, so now I think I've got the implementation to compute the sum, the difference, and the maximum of each list element-wise by pairing up elements. We'll try compiling that again. We no longer get those warnings, and I'll try running it. And I think it works. Okay, our sum is what we expected it to be, 16, 222, 298. The difference, you can check that on your own, but I'm going to claim it's correct. The maximum is also what we expected it to be. All right, so I'm going to clear my diagram from the lower right because hopefully we now agree that all of the functions work correctly. And the issue here is that we have redundancy. And we know redundancy is bad. We've known that since the beginning of 111, that if we have redundancy, we need to eliminate it. And in week 2 of 111, we didn't want to copy and paste code, so we learned about how to write loops. In week 3 of 111, we didn't want to copy and paste code that we use in different parts of our program, so we learned how to write functions. In 116, we've also learned various ways to avoid redundancy. So one of them is writing classes, using encapsulation or abstraction to avoid having to repeat behaviors or to allow flexibility. It turns out that to some extent, classes might help us a little bit with the redundancy we have here, although it would still be pretty bulky. And we do that via subclasses. We do that with inheritance. We've also seen templates can help us avoid redundancy. What I would like to demonstrate in the rest of this video is that none of those techniques will really help us that much here. So the first question is, okay, what is similar between these various implementations? The differences are all showing up inside the loop. The outside is where the similarities show up. There is a small difference showing up in the return type, but other than that, all of the actual different behavior is buried in the very inside of the code. In list maximum, I have this. In list difference, I have this. And in list sum, I have this. And then in pair up, I've got something a little bit different, but not too much different. Still pretty much the same. The machinery outside of it definitely is identical. So what do I do? Can I use functions for this? Now, if I were writing a whole bunch of different loops that all had the same contents, so the loop body was exactly the same, I had, the same few lines in my loop body over and over again, and I had different loops, then I would write a function to do what's happening inside the loop. That's a classic application of functions. But a function can't quite help me with what I have here. Here, what's happening on the inside is different, and what's on the outside is the same. I can't easily write a function to do this stuff, and then, how do I pass in the different code that I write on the inside? Well, I can't do that with functions as we remember them from C. Okay, well, I guess I could argue loops might help us, but we're already using loops here. They're not really helping that much as it is. What about templates? Could templates help? And the answer is, well, no. There are lots of reasons templates might be helpful for an application like this. An example being, maybe later I want to not just add up lists of ints, but also lists of floats. A template could certainly help me with that. But a template can't quite help me with decoupling the inside of the loop, the behavior that's happening for each pair of elements, from the behavior I use to actually get each pair of elements. Okay, could classes help us with this? And the answer is sort of yes. So I could write a class that contains a member function where I pass in 2 lists. And inside that member function, it does all of this stuff. And then in the middle, where I want to have my own behavior, it calls its own other member function that actually does the operation. So it passes in what's in iter1 and iter2, what they point to, and some other member function performs that. I could define that member function to add them together, for example, and return it. And then maybe I could define a bunch of derived classes that override that behavior to change what's happening in that member function for each of the different applications, difference or maximum or sum. That would work. I'd end up with an abstract base class with a virtual function and a bunch of derived classes that override it. So that's a high-level overview, but that would sort of work. It would be a little bit clunky. There'd still be some reasons why there are some difficulties with it. In particular, how do I change the return type if I need to? But that is a viable option. If you were to see it, you'd probably agree that it's viable, but it's still pretty tough. It leaves a lot to be desired. What I really want, though, is something pretty simple. I just want the ability to decouple what I'm doing inside the loop with how I'm getting there, so the loop itself. I want to decouple those 2 pieces without judgment. So what I'm doing with my usual functional decompositions we've seen in 111, for example, were a decoupling that only works in one direction. I'm allowed to make a function to represent what's inside the loop, but if I want the same loop over and over with minor modifications, I may have to just keep rewriting it. Instead, I want to be able to separate those into 2 equal pieces, the outside and the inside. I want to fully decouple those behaviors. And to do that, what I'm going to use ultimately is functions. But they're functions I'm going to treat in a way I haven't treated them before. Now I'm going to begin treating functions like data. And that means I can give them names like I give a variable a name. I can pass them into functions. I can make them class members. I can do anything that I could do with any other piece of data, but I can do it with a function. And we'll start talking about that decoupling process in the next video.